This video is part of a series on the xv6 operating system kernel. In this video, I will cover the functions and walk through the code in the file fs.c. There are a large number of functions, and I've broken this into two separate videos. Each is about 45 minutes long, and this is the first video in that series. In the previous video, I introduced the data structures and gave a summary outline of the functions, and in this video, I'll go over the code in the functions. But here, let me just review this list. These are the functions that I will be covering in this video, and I just will present this material here on the screen so you can have a reference as to what is covered in this video. These functions are all covered. BMAP I will cover in part 2. However, in this video, I will cover itrunc and stat_i, and then the other functions, read I, and so on, will be covered in the next video. And in the next video, we will end up talking about the main function, name_i, which is sort of what we're working toward. It's passed a pointer to a path name string, and it figures out which file on the disk that is, and returns a pointer to an inode representing that file. Okay, let's get going. Let's start with the functions that are involved with initialization. So here's the main function. This is from file main.c. And recall that it tests the core, and all of these functions are executed on core 0. That is, they're executed only once. And these functions are executed by the other cores. And after all of this, we start scheduling. Right here we see binit, which initializes the data that's associated with the buffers. And then we call init. Remember that the inode cache consists of an array. It happens to have 50 structures in it, and the structures are inodes. And there is one spin lock that protects the entire array, and each structure has its own sleep lock called lock. So here is the code for init, and you see we're initializing the one lock that's associated with the I table, and then we're going through the entire array right here and initializing each of the sleep locks. These structures also have a reference count, and if this is 0, that indicates that this element is unused and available for use in the future, and the reference field is initialized to 0 by default. Okay, going back to main, we see a call to file init. This, I haven't talked about this yet, but essentially this initializes a lock as well. And we do some initialization related to the device. And then we create the init process. So here we create the first user process. And at some point, we will start scheduling, okay? And one of the cores will pick up this process and will begin the very first time slice. We can't do any disk I/O until we are actually running in a user process because the disk I/O stuff needs to sleep. So let's take a look at what happens when init is first executed. Well, remember that forkret from the file proc.c will be called to schedule the first time slice. And it contains this code here that asks whether this is the first time it's ever been called, right? There's this local variable, sorry, there's a static variable that's initialized to true. And so the first time this function is called by any process, it will execute this code here and then set first to 0. And what does that do? Well, it calls fs_init. So let's take a look at fs_init. Now we're running inside of a process. And here is fs_init. I'll read SB2. The first thing it does is it calls read SB, which will read in the superblock from the disk. So here we see a call to bread, and this will be the first read we do, and sets BP to point to the buffer. And then it moves data from the buffer. And how much does it move? Well, the size of this superblock structure, and it moves it into this superblock structure. We're passing it the address of that superblock structure. And then we release that buffer. So after this point here, we have the superblock variables stored in that superblock structure, and we can access things like the magic field. So we immediately check it to make sure that the device contains a file system of the type that we are expecting, that the file system has been properly initialized and so on. And then we call init log. And I discussed the logging system in a previous video, but this is where that gets called. So after this, we can create transactions. That is, we can call begin op and end op and log write. Next, let's take a look at the function Ialoc. Every time we create or grow a regular file or a disk file, we need to find an unused block on the disk and zero it out and then add it to the file. So Ialoc is called to allocate and zero out a disk block, and it will return the number of the block that it found. So basically it's going to search through the bitmap for an unused block. Remember that our bitmap here can, in general, consist of several blocks, okay? With only a tiny disk with 1,000 blocks in it, it'll only have one block, but in general, this code will search a number of blocks. Okay, so this code can accommodate a much larger disk. So it's got, let's look at the structure of this thing. It's got two nested for loops, okay? And the first one will go through the blocks, and for each block in the bitmap, it will read that block. And then the next loop will go through all the bits in the block, looking for one that is free. Okay, so here this outer loop has an index variable of b, and it's being incremented by the number of bits in a block. Well, there are 1,024 bytes with 8 bits each, so it's b goes from 0, and then 8k, and then 16k, and so on. Okay, so each one of these will be a block, and the first thing it does is it reads that block in from the device. Okay, this function bblock is passed a block number as well as a pointer to the super block, and it will figure out which block on disk contains that bit. So we read the first block and then the second block using the bit at the beginning of the block as the index here. This inner loop runs through the bits within that block. So it goes from 0 up to 8191. So that's this loop index here. It's incremented by 1. However, so the actual bit that we're looking at is this number plus the index within the block. Okay, and that's b plus bi. And of course, we also stop if we hit the size of the disk. If we search through all of the bits in the bitmap up to, well, in this case, we have only 1,000 blocks. So if we search up to this point without finding anything, then we immediately abort, and that causes us to panic and say that we're out of blocks, that the disk is full, there are no free blocks. So once we have a bit number within the block, that's bi, we need to figure out which bit within the word, or within the byte, I should say. So we are using mod 8 to figure out which bit within the byte, and divide by 8 to figure out which byte within the block. So here we create a mask, all zeros except for one bit in the appropriate position. And so that's our mask. And it's a byte, although it's declared as a 32-bit value. We're only concerned about the 8 bits in it. And then here we are looking at one individual byte and ANDing it with the mask to look at one particular bit. And if that is 0, then this indicates it's a free block. Okay, 0 is used to indicate free, and the 1 bit is used to indicate in use. So if we find a free block, then the first thing we do is we set the bit. So here we're taking the same word and we're ORing it with the mask to set that 1 bit to a 1. And then we are writing the block back. We've changed this one block in the bitmap, so we need to write it back to the disk. And we do that here. And then we release that block. And finally, we zero that block. So here we are using b plus bi. That's the actual block number that we found that is free. So we're passing this block number to the B0 function, and then we return the block number here. And I just want to say that after we've searched this entire block and not found any free bits, then we release that block and we move on to the next block in the bitmap. So this B0 function is right here. It's only called from Ialoc, where I just showed you, and so you can more or less forget about it after this. But what it does is it is passed the block number, okay, and it reads that block, getting a buffer pointer to the buffer that contains that data. And here we are updating the data, and in fact we're using this function memset to move a bunch of zeros. How many zeros? Well, the block size is 1024. So we're moving that many 0 bytes into this data area, and then we're writing that block back to the disk. And finally, we're releasing that buffer. Now, so these functions here are calling bread, logwrite, and brelease. Okay, so that means they must be within a transaction. So we'll see that all of the functions in this file here are supposed to be in a transaction. They will call bread and logwrite, and we assume that all of this is happening within some transaction. So this code outside of the file fs.c will begin the transaction and then call these functions, or some of these functions, and then ultimately call the end op function to terminate the transaction. As a professor, I can't help but insert a little commentary at this point. This algorithm is pretty straightforward and easy to understand, and for our purposes of xv6, it's adequate. But I have some questions about efficiency. For one thing, it's searching every bit in the block one by one. So this inner loop is executing 8K times. And for each execution, it's building this mask and then doing a little bit of computation. Now, when we allocate a block, we need to search through all the bits until we find a bit that is 0. And so we might have a bunch of blocks that are in use. So we go through a bunch of bits that are 1. One approach would be to look at entire words at a time rather than individual bits at a time. So the idea is that we would have a loop that would loop through all the words in the block, and it would look at each word and ask, is this word equal to a word with all 1 bits? And if it is, then it doesn't contain any 0 bits, so there are no free blocks represented by that word. So we can move on to the next word. So it searches word by word instead of bit by bit. And then when we finally find a word that is not all 1s, it must contain a 0 bit. So at that point, we search the word and find out which block is actually free. But still, there's a problem. This is doing a linear search. If the disk is almost entirely full, we have to search through the entire bitmap. And for large devices, that could be time-consuming. So we don't really like to do linear searches in the first place. I want to just mention another approach to managing free lists. So the idea is that we keep a linked list of pointers. And so each one of these structures represents a block on disk, okay? And each block contains 256 words, shall we say. The first word points to the next block in the linked list, and the remaining words in the block point to free blocks, okay? So in order to get a free block, we go to this linked list, and maybe these have been allocated, but here's the first block, so we can allocate that one. And that's pretty quick because we just keep a pointer. It's a stack, basically. When we return blocks to the free pool, we push onto this stack, and then when we allocate blocks, we pop off of this stack. And then when we get to the end, okay, after we allocate this block, the next allocate, well, we just allocate this block itself, the entire block, and now this block becomes the head of the list. And we begin with our stack pointer here, and when we want to allocate a block, we allocate this one, and then this one, and then this one. These blocks will be kept on disk, and you can see that these are each one of these requires a block, but we have a bunch of free blocks anyway, so it's not really a cost to store this linked list on disk. As we consume blocks, as blocks are allocated, we consume the blocks that are used for the linked list as well. And we would also like to keep one or two of these blocks in memory to make this process faster. So we can keep allocating here, we can allocate this block, and then we can allocate this block, and we can keep going. But at some point, we have to read in the next block from disk. And likewise, when we're returning blocks, we can fill up this block, and after this block is completely full, well, we need to write this one back to disk, and we just have returning a block, so we actually have a place to write it. So we have a slightly complicated algorithm, but it's going to be much more efficient because returning a block will normally involve just writing a number into this and advancing the stack pointer, and allocating a block will be just grabbing the next element on this and decrementing or increasing the stack pointer. The one aspect of the free block being kept as a bitmap is from time to time you want to allocate a number of blocks and you want them to be close together on the disk. For example, when we allocate the blocks for a file, we would like all those blocks to be close together because if one is read, it's quite likely that the others will be needed as well. This approach here doesn't really deal with that, whereas with the bitmap, if you're trying to allocate, let's say, 10 blocks altogether, then you can search the bitmap for a place where you find 10 0 bits, that is 10 free blocks altogether. And so there, we can go down a rabbit hole here, but I just want to point out that this code is simple and easy to understand and adequate for the xv6 teaching kernel, but in reality things are going to get quite a bit more complicated. So now let's turn to looking at the corresponding free routine. From time to time, files are deleted or their size is reduced, and we need to return the blocks in the file to the free pool. And for that, we have the bfree function. When we allocate a block from the free pool, we have to search the bitmap to find an unused block. But when we free a block, we just need to find the corresponding bit in the bitmap and change it. So bfree is passed the block number, and it calls bblock with that block number to determine which block in the bitmap will contain the corresponding bit for that block. And then we read that block from the bitmap area into a buffer. And here we compute the bit within that block. So this is bits per block. And we use the mod operator to figure out a number between 0 and 8191 within that block. Then we use the mod and the divide operator to figure out which bit within a byte and which byte within the block. So here we are making a mask, all zeros except for a single 1 bit in the corresponding position using the mod operator. And here we are figuring out which byte within the data block will contain that bit. And we're looking at that, so we're ANDing it with the mask to determine the value of the bit. 0 is used to indicate free, and if it's already 0, we've got a problem, so we panic. But otherwise, we set the same byte by ANDing it with the not of the mask, right? So we turn all the 0 bits into 1, and so that preserves them. But the bit that we're interested in here turns into a 0, and by ANDing it, we clear it. So this sets the, or I should say, clears the bit that we're interested in to 0. And then we write that buffer back to disk and release the buffer. Next, I want to talk about the iGet and the iPut functions, as well as the iLock and iUnlock functions. Whenever we want to access an existing file, we'll call iGet and iLock, and then when we're done with it, we'll call unlock and iPut. So iGet is passed an inode number, as well as the device on which we want to find this file, and it returns a pointer to that inode in the cache. So it will look in the cache to see if we already have that inode open, if you will, and if we do, we'll use that one. Otherwise, it will allocate a new entry in the cache and devote it to storing that particular inode. But in any case, it will increment the reference count to indicate that that structure in the cache is used for that particular inode. It won't read in the inode from disk, and it won't lock the inode. To do that, we call Ialoc, which will lock the node. And then if it has not yet been read in from the disk, it will go ahead and read it in. So then when we're done using this particular inode, we call unlock, and it will unlock the node. And we can call IPut. Okay, IPut will decrement the reference count. So if it was already there, when we called iGet, we incremented the reference count. And then when we're done with it, we call IPut, and it decrements the reference count. And it checks to see whether we have no more hard links to it. And if so, it gets rid of the file. But otherwise, the file will stay in the cache. If it decremented the reference count to 0, then that node or that structure in the cache is now available for reuse. But if there are other users of the inode in the cache, then the reference count will not yet be 0, and it will persist for the other users. So let's first take a look at the get function, which is here, iGet. Find the inode with the number inum on this particular device, and return the in-memory copy, okay? But it will not lock that, and it will not necessarily read it in from disk. Okay, so in order to access the inode cache, we need to lock the itable lock, and then we have a loop that's going to search the cached inodes. So here we start with 0, and we go all the way up through all 50 of them, and we look at each one of them. So what we're doing here is, in this picture, we're acquiring this spin lock, and then we're going through all 50 of these structures, and we're looking for one that matches the device and I number. Okay, so we're looking for one that, in this loop, we are looking for one whose device matches the device we're on and whose I number matches. And we're looking for something that is not free. So if it's the reference count is greater than 0, then we've got one, and we increment the reference count, and we release the lock and return a pointer to that inode. Okay, but we might not find one. So as we go through all 50 of these structures, we look for one that has a reference count of 0, and if so, we save a pointer to that one in this variable empty. And here we're checking to see whether we've already found one, and we only save the first one. And then we exit this loop if we haven't found one, and we are recycling or allocating a new entry in the cache for this particular inode. Okay, so we make sure we have enough. We actually found one. Otherwise, we've run out of inodes in our cache, and that's cause for panic. But if we find one, then we are pointing to it, and then we set its device and I number to indicate that it's in use, and we set its reference count also to indicate it's in use. So now we have allocated it, and we set its valid to 0. Now, previously I said that the valid field was protected by the sleep lock of the structure itself. So this sleep lock, called lock here, protects everything below it, including the valid field. So is this cool that we're modifying the valid without holding the sleep lock on this? Well, we are the only process that is accessing this inode, okay, because the reference count is 1 here. We just set it to 1. And we are holding the itable lock. So no other process could conceivably get a pointer to this particular cache because the reference count is protected by the lock. So setting valid to 0 here is safe. Okay, next let's look at the lock function, the Ialoc function. So it's passed a pointer to one of these cached inode structures, and it is making sure that the reference count is really 1 or greater, and if not, it panics. Okay, now we are going to modify the fields of it, so we need to begin by acquiring the sleep lock, and this will uh, uh, lock it, and once we've gotten the sleep lock, we check the valid bit. If the valid flag indicates that we have not yet read the data in from disk, then we need to do that. So here we call bRead, and we're reading from the device, and the call to iBlock, which I should have bolded here, is called to compute which block on the disk this the inode is kept in, and then we read that block. And here what we're doing is we're moving everything from the inode structure in that block into the cached version pointed to by IP. So we're getting a pointer to the inode in the block. So here we're accessing the data of the block, and we're figuring out exactly where in that block this particular inode is stored. This is inodes per block, so we're figuring out that. So back in this picture, we're just basically computing where in the block we need to read from. And that's the pointer for the source. And then we're copying the type, major, minor, in link, size fields, as well as the address array here. Okay, so here we're copying the address field from DIP to the cached copy. And finally, we're releasing the buffer that we use to read in the inode from disk and setting the valid flag to true. And we're also making sure that the type that we just read in is not 0. We shouldn't be reading in a inode that's not allocated. Okay, so unlock is pretty straightforward. The Ialoc function is passed a pointer to one of these cached inodes, and it just releases the sleep lock. Okay, it does a little checking here to make sure that we have a pointer and we're actually holding the sleep lock, and the reference count can't be 0. We better be referring to it. And so then we release the sleep lock. So next, let's take a look at the iPut function. Okay, remember what the iPut function is going to do. It's going to decrement the reference count. And if that reference count is now 0, that means no other processes are using the cached copy, and the number of hard links to this file is 0, then we're going to eliminate the file. We're going to truncate it to link 0, set its type to 0, and update everything on the disk. And finally, unlock the inode with a reference count of 0. The cached structure will now be free to be reused for some other inode. So let's take a look at the iPut function. When a process is done with a file, it's done with the cached copy of the inode, and we need to allow other processes to use the memory in the cache for other inodes. So let me read this. What we're going to do is drop a reference to an in-memory cached copy of an inode. If that was the last reference, then the cached space, the space in the cache, can be recycled. And furthermore, if that was the last hard link to the file, then this inode is not reachable. And so we need to free both the inode and all of its data and its block of indirection as well, if it has one. So as is true of all the functions in this fs.c file, this function must be inside a transaction. Okay, so it's passed a pointer to the cached copy of the inode, and it's going to acquire a lock on the cache because we're going to be modifying the reference count. So the way this is actually organized is a bit different than I showed in my handwritten stuff. We have the if statement first, followed by the decrement of the reference count, and then we release the lock on the cache. The reason we want to decrement it last is because if it turns out we're going to be deleting the file, we want to maintain a reference count of 1. So here we're looking to see whether we have a reference count of 1. That is, we are the last process that is accessing this cached copy of an inode. And if that's the case, and the number of hard links is 0, then we can go ahead and delete the file. Okay, so we will be truncating it to length 0 and setting its type to 0. In order to modify the type, we need to be holding this inode's sleep lock. So here we acquire the sleep lock, and here we release the sleep lock. And then we call itrunc, which will look at this inode, and it will look at all the data blocks it points to, either directly or indirectly, and it will eliminate all of those, or I should say it will return those to the free pool and update the bitmap and so on. And then we set its type to 0. So that makes it an unused inode. Previously its type was either regular file, directory, or device. And by setting its type to 0, we indicate that it is free. But this is the in-memory cached version. So here we write that to the disk. So at this point we are updating the disk, and now the inode that's stored on the disk will also have a type code of 0. And then we set the valid bit to 0. So now here we are releasing the lock for the cache and then reacquiring it right here. We need to be holding the lock for the cache before we access the reference count. So we need to reacquire it if we release it. Why do we release it? Well, as far as I can tell, there's not a deadlock concern. We're not releasing it for that reason. And I think it would be legal or valid or correct to just hold on to this lock. You know, after all, we've acquired this lock, and we're not acquiring any more locks. We can release this lock here or not, but there's no problem with holding on to it as far as I can tell. But it's if we do release it, we need to reacquire it, of course. But it's just a question of politeness. Okay, we're going to be calling itrunc, and that's going to be doing some disk writes, or more precisely, it's going to be calling log write and bread, which will need to allocate buffers and modify the log and so on. Could end the update, it's the same thing. We're going to be calling log write to update the log file. All of this stuff could take a little while. The cache of inodes is somewhat of a bottleneck. It could be that the cache holds the inodes for some very important and popular files, and so we'd like to release this spin lock as soon as we can. I think that's why it's released here, but then of course it's reacquired. Now, then we have the question of why is valid being set to 0 here? We've already set type to 0, which indicates that this inode is unused. But if you look right here, there's a moment of vulnerability. Okay, we've released the spin lock and we've released the sleep lock. So at this point right here, we're not holding any locks. And we haven't looked at Ialoc yet, but what Ialoc is going to do is look on the disk and find an inode whose type is 0. And so it might find this very inode, the inode with the same number that we just wrote out here, and it might say, oh, okay, I'm going to recycle that for some other file. And then what it will do is call iget to see if there's already a cached version in memory. Okay, and so there is a cached version in memory, so we need to make sure that it doesn't get used. So that is why we need to set valid to 0 right here. Okay, the reference count is still 1, so when we look for it in the cache, Ialoc will find it, or it might find it, and try to reuse the cached version. Well, the cached version is not correct. Ialoc will have modified the type on the disk, and it needs to read that back in so that the type in memory is also adjusted. And we can't do that here because we don't know what the type is. So I think that's why we are setting valid to false right here. So I hope that explains iPut. The other function we have down here is called unlockPut, and all it does is unlock an inode and call put. So it's very common that after we've modified or used a file, we are ready to both unlock its inode and get rid of our reference to it. We're all done with it. So this is a common idiom. Next, let's take a look at the Ialoc function. This is called whenever we want to create a file. We pass it the device that indicates where we want to create the file. and the type, which will either be a regular file, a directory file, or a device type. And what this will do is find an unused inode on the device and mark it as allocated by setting its type field to whatever we were passed here. And then it will call iget here to return a cached copy of that inode. Okay, so let's go through the code here. We are going to loop through all possible I numbers. We skip 0 because 0 is not a valid I number. And so we go from 1 all the way up to our maximum number. In our example, we have 199 possible inodes. So we loop from 1 to 199. And for each one of those, we need to read it from disk. Okay, so we'll call bread. iBlock is passed the I number, and it will determine which block this inode is stored on. So the first one, number 1, will be stored on this block, which happens to be block 32. And so we'll use block 32 for several, and then we'll go to block 33 and so on. So then we compute, once bread returns, it has a pointer to the buffer that we've read in. And we then figure out where in that buffer we can find this particular inode. So here's the pointer to the data of the buffer, and we take the I number modulo the inodes per block, and that tells where in the buffer we can find the on-disk data for this inode. And then we look at its type field, and if that's 0, okay, then we found one that's free. Okay, if it's not 0, then we release this buffer and loop back to the next I number and call bread again. Now, most likely, when we call bread the next time, the block that we need is just sitting in the buffer cache. Okay, we just read it previously for the inode before this, and this new inode is probably on the same block, so we don't actually do a disk read for most of them. So we just loop through the inodes in one block. Eventually, we hope to find one that has a type of 0. If we don't, and we get all the way up to 199, then we'll exit this loop and panic that we have already allocated as many files as we possibly can. I think earlier I said we have a maximum of 200 files, but since we don't use 0, we have a maximum of 199 files. Okay, so let's say we find an inode with type equal to 0. Then what we're going to do here is zero out all the fields in the inode on disk. So we copy zeros into this buffer, and here we're doing that. This is the size of the inode on disk, and then we set the type field to whatever argument we were passed, and we write that buffer back to disk and release it. And now that we've got the inode updated on disk, we call iget, and iget will look through the cache and find an empty slot for this inode, and then it will fill in the device and I number, as well as setting the reference count to 1, and it will return a pointer to this in-memory cached version of the inode. The valid flag will still be 0 because we set it to 0 earlier, and so unused entries in the cache will have a valid flag being equal to 0. And when we call iloc, we will go ahead and read the data in from disk and copy it into this area. Ialoc is only called from the create system call, and that system call will immediately call iloc. So it will read the data from the disk, okay, and it will copy it into the cached structure. And since the block is probably still sitting in the buffer, it won't involve a second read of the disk. Whenever we update the inode associated with any file, we need to write those changes back to the disk, and that's the function of the iUpdate function. So it's passed a pointer to some cached inode, and it will write it to disk. So copy a modified in-memory cache version of an inode back to the disk. It must be called after every change to a field in the inode that is stored on the disk. And the caller of this function had better be holding the sleep lock associated with this inode. So we saw that this was called in the I_put routine. So here's the I_put routine. Remember, if we're going to delete the file, we set its type to 0 and then immediately write that to disk. So here's an example where we call I_update. The code is pretty straightforward. First we invoke iblock, giving it the I number of this particular inode, and it computes which block contains that inode, and then we read that block from disk into a buffer. Okay. Then we compute where in that buffer we can find this particular inode. So we take the I number modulo the inodes per block, and then add that as an offset to where the data is for that block. And that gives us a pointer into the buffer. And so then we set the type, the major, the minor, the inlink, and the size, right? We set the type, major, minor, inlink, and size. And then we set the address array. So we copy it from the cached copy in the itable cache. Okay, so we're copying it from this area here into the buffer, and then we'll write the buffer back to disk. So that's what we're doing with these copies. And here we're copying the address array. The size of this array is 13, that is the number of direct pointers plus one more. And then we write that buffer back to memory and release the buffer. From time to time, we need to truncate a file to length 0. That is, we need to get rid of all of its data. One place we do this is in the I_put function. So here's the I_put function, and if we've determined that the number of hard links to this file is 0, we're going to go ahead and delete the file. So we call iTrunc or iTruncate here, and then we go ahead and set the type to 0 and so on. Another place that iTrunc is called is in the open system call code. We have the option there of truncating the file to length 0. So let's take a look at what this file does. The caller must hold the sleep lock on the cached version of the inode. So it's passed a pointer to the inode that's cached, and it's going to go through that inode and look at all the data blocks it points to. So here's the picture. It's passed a pointer to one of the cached copies, and it's going to go through this array here. And let me use this array up here because it has the blocks. So we're going to go through the direct pointers, and if they are non-zero, we're going to call bfree to return this block to the free pool. And then we're going to go through the block of indirect pointers. So that's what's happening here. We go through the direct pointers. In our case, we have 12 of them, and so it's from 0 to 11. And we look at each entry in the array in this inode, and if it is non-zero, then it has a pointer, and so we need to call bfree using that block number. And what this will do is update the bitmap to change the bit for this block from 1, meaning in use, to 0, meaning free. And then we zero out the element in the array. And so after we've done all the direct pointers, we need to ask whether there is a block of indirect pointers. So we ask whether this pointer here is 0 or not. And then if it is not 0, we need to read this block and then go through all of these pointers, free each one of these, and then free the block itself. So that's what's happening here. We ask, is the last element, okay, that's the 13th element, or we have 12 direct pointers, so element number 12, which is the 13th element of the array. If it is non-zero, then we have an indirect block. So here we call bread to read that indirect block into some buffer. And here we find where in that buffer the data is actually stored. Okay, and that we will consider to be an array. Okay, it's considered to be this array here, and we're going to index through it. So in this loop here, we are indexing from 0 up to, well, in our case, we go from 0 to 255, and we look at each element in the array and ask if it's non-zero or not, and if there is a pointer there, then we call bFree, providing that block number, and that will free the block. So we go through this array one by one and free these blocks, and then finally we release the buffer that contains the indirect block. Okay, that's this buffer. And then we need to free that block itself. So again, here is the address or the block number of the indirect block, and we just call bFree with that block number to free the indirect block, and we set the final element of the array to 0. Then we set the size in the inode to 0, and we update the cached version of the inode by copying it back to disk. Okay, we've also got this function here, stat_i, which is simply going to copy some information from a cached inode to someplace else. Okay, so we've got a stat structure, and we assume that we are holding the lock on the cached inode because we are reading the fields in that cached inode, and we're just copying them into this stat structure. Okay, we've just covered about half of the functions in the file fs.c, and the remaining functions will be covered in the next video, so I'll see you there.